No questions? Okay. Then we will start with today's work. Last time we finished the analysis of stresses due to press and shrink fits. I don't know whether I mentioned this or not, but some students ask me about the von Mises stress. And remember that I said that von Mises stress is really not a real stress and it doesn't act anywhere on the material. And so they were looking for something tangible. Is there anything that we can say, here, this stress is acting on the material? I don't know whether, again, I don't know whether I mentioned this or not, but if you read your book, there is a section, a very small section, right at the end of von Mises' discussions, that talked about octahedral shear stress. Octahedral shear stress is a stress that actually does occur in the material. Let me just say a couple of words about that before we start today's work. When you have a three-dimensional state of stress at a point, let's say with principal stresses, then the maximum shear stress that you find from any Morse circle can be found numerically from two of these. Is everybody following me? In other words, the radius of three Morse circles can be found if you take sigma 1 minus sigma 2 divided by 2, sigma 2 minus sigma 3 divided by 2, and sigma 1 minus sigma 3 divided by 2. Everybody okay with that? Any questions? And remember, if you have a question, please ask, because something like this I may ask you in an exam. There will be a conceptual part in your exam, so these questions will come up. So if there's something you don't understand, please tell me. On which planes do these shear stresses act? So if we have this, for example, one of the three Morse circles could be this. Sigma 1, sigma 2, there's the Morse circle. So where does the maximum shear stress act with respect to sigma 1 and sigma 2 in that Morse circle? Well, not in that Morse circle, it's not out of plane. This is the maximum shear stress, right? How is it oriented? On which plane does it act?
It's 45 degrees from that plane.
From the planes of sigma 1 and sigma 2, that's right. 45 degrees from the planes of sigma 1 and sigma 2. So here is sigma 1 and sigma 2, so that maximum shear stress acts on this plane. Let me Everybody okay with that? 45 degrees to sigma 1 and sigma 2. The other two possible maximum shear stresses also act at 45 degrees with respect to these two and then these two. So you get three planes, all making 45 degrees with two of the three principal stresses. The octahedral shear stress is a stress that acts not on these planes, it's not a maximum shear stress, but on what are called octahedral planes. Excuse me, and that is this plane. That's the octahedral plane. And there is a theory of failure called the octahedral shear stress theory of failure, which says that yielding will occur when the shear stress on this plane, the octahedral shear stress, reaches that at yield in a simple tension test, just like the definitions that we had before, except that it's not the maximum shear stress, it's the octahedral shear stress. And this is a real shear stress. It does exist. And the answer that you get from this failure theory, the octahedral shear stress failure theory, is exactly the same as that which you find from the von Mises. So if you're trying to find something quote unquote tangible, insofar as the von Mises stress is concerned, this is it. But of course we don't use this in real life because although it's possible to find the shear stress on that plane, it's not very easy, not a very friendly thing to do. So rather than doing that, we calculate the von Mises stress, which actually is not a real stress in the material, but gives us the same answer anyway. So that's, if you're looking for something that actually exists, that's it, the octahedral shear stress. Okay, today we will look at contact stresses, sometimes called Hertz stresses or Hertzian stresses. In applications that we have, many times you find that two parts are in contact and especially roll against one another in real life examples. And you know many examples of this. So an example of two parts rolling? Roller bearings, ball bearings, either one. Gears. You've all had 233. These should be questions that you should be able to answer very easily. This is what gears do as they mesh. In this case, they don't just roll. In the case of gears, they don't just roll. They roll and slide. In some cases, they just roll. And invariably, as the case of gears or bearings, they transfer load as well. So for example, if you have a ball bearing like that, then you have a shaft in here, and the shaft is carrying load and passing this load, let's say, to a support. This bearing is sitting in a support, like a pillow block, for example. And the shaft is rotating, and these balls are rolling both on the inner race and on the outer race. They are also transferring load. So if the assumption is that there's a load in the shaft right where this bearing is, a reaction at the bearing, and that load looks like this, every time one of these balls comes in here, it takes the brunt of that load from the shaft. And as it passes that point, that load is released. And then the next time around when it comes back, the same thing happens. The same thing is true about the racers. They see this force or load as well. These loads lead to stresses, which can lead to failure of the material, either by yielding or by a repeated process of loading and unloading, which is a type of fatigue failure. And we'll take a look at fatigue in general in detail. This one is a special case, so I'm just introducing it now because it is a part of contact stresses. So, having said that, consider what's on the screen: two spheres in contact and a load applied between the two. And at this time, let us assume that there is no rolling action and that the forces that are acting and the stresses that are developed are static. If we have two spheres in contact like that with a load applied, there will be an area called the contact patch between the two due to the deformation of the two parts. That's this area right here, that little small area right there. What's the shape of that area if you have two spheres in contact? So we have, just think of this, you have two rubber balls, sphere, put them together and push them. The area of contact has what shape?
A circle.
A circle. Is everybody okay with that? Area of contact is a circle. Of course, these are not rubber balls, they're probably much harder. And the only difference is between this and the rubber ball is that the contact area is much smaller here, but it's still a circle, because that area is introduced due to the deformation of the two parts. We can calculate the radius of the contact area or contact patch using theory of elasticity, and we will get this. A equals the cube root of 3f over 8 times 1 minus nu 1 squared over E1 plus 1 minus nu 2 squared over E2 divided by 1 over D1 plus 1 over D2. In this equation, A is the radius of the contact patch, F is the load that's being transmitted between the two spheres, nu1 and E1 are the elastic properties of sphere 1, and nu2 and E2 are elastic properties of sphere 2, and D1 and D2 are their diameters. Once you have this, you can also calculate the maximum pressure that is developed between the two. And we'll take a look at that in just a second. If the contact, rather than being between two spheres, is between a cylinder and a flat plate, not cylinder, sorry, sphere and flat plate. We haven't gotten to cylinders yet. Sphere and a flat plate. Can we use this equation to find the radius of the contact patch? Contact patch is still a circle, is it not? If you have a flat plate and you push that rubber ball on it, the contact patch is still a circle. So can I use this equation to find it? Can you define a straight line as a circle? No, why not? Straight line is a circle. Sure. Each of these has its center farther apart from the arc that I'm showing, right? Small diameter, larger, 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 infinite. So yes, you can show a flat plate, call it a sphere, of infinite diameter. Would you expect this to give you a larger contact patch or a smaller contact patch than that? If the two are spheres, here one is a sphere, one is a flat plate, which one will give you, everything else is the same, except for the flat plate and the sphere. Which one gives you a larger contact patch? I'm sorry? What do you mean two?
You said which one?
Yeah, which one are you calling two though? Plane and a sphere. That's right. That's right. The plane and the sphere. You should be able to actually see this by envisioning this. Two spheres rather than a sphere and a flat plate. The flat plate gives you a large area. But you can also take a look at this equation. One of these two becomes infinite. So this denominator decreases. Therefore, A increases. Okay? So we can use it for flat plates. How about this? A sphere inside a spherical cavity. Can you use this equation? Well, first let's ask this. Do you expect the contact patch to get larger or smaller? Larger, okay. Can you use that equation? Sure. Of course you can. Positive radius of curvature, on this one, as compared to this. Positive radius of curvature, zero radius of curvature, infinite radius of curvature, negative radius of curvature. So this basically has negative radius of curvature. So one of these becomes negative, whichever of those two it is. Once it becomes negative, of course, the denominator of that equation decreases yet, and therefore you get a larger value for A. Any questions? Having these, and having found the radius of the contact patch, we can calculate the maximum value of the pressure, which is the force over an area, a pressure, that acts on the contact area. We say maximum pressure because the pressure is not uniform across the contact patch. The contact patch is circular like this. And the pressure distribution is like this, with the maximum value occurring here. And as you get away from that, smaller values here, here, there, and there. So what we're calculating there is the magnitude of the pressure at the center of the contact patch, P max. This, of course, this pressure sets up stresses. Clearly, a stress in the z direction is obvious, as you can see. By z direction, I'm referring to what's on the screen, the coordinate system that's given. X-axis, y-axis, and z-axis. So the force is applied here. There's clearly a compressive stress in between these two on the contact patch area, whose maximum value occurs at the center of the contact patch. And of course, whose maximum value is obviously equal to P max. And we'll see that as we take a look at the stress distribution as well. So there is no question that there's a stress in the z direction. Are there stresses in the x and y direction? There are or there are not? What happens if you... How does this deform? A little cylinder under compressive load. What happens to its length? Come on, guys, you need to wake up. We're not going to go anywhere unless just looking at me is not going to work. You have to think and you have to answer my questions. It doesn't matter if you're right or wrong. This is not for a grade. But you've got to have some idea. And if your idea is not right, I really need to know that. Otherwise, things will not progress. So, what happens to the length of this? Decreases. Okay, so that should be obvious. Is there any other change in any other dimension? Poisson's ratio, right? Okay. If there is nothing supporting this, this will grow laterally. But right here, here's the stress in the z direction, epsilon in the z direction, and then epsilon in the x and y direction. There's a whole bunch of material supporting that. So this change of length in this direction, the change of length in this direction becomes tough to do, meaning there's a stress, compressive stress, preventing that change of dimension. Not that it doesn't exist, it does exist. It's just not as much as it would have been if this were free to change length. Therefore, stresses in the x and y direction are also set up. All of these stresses are compressive, and all of them are principal stresses. So sigma x, sigma y, sigma z are all compressive, and they are all principal stresses. The equation for sigma x and sigma y, and this is again from theory of elasticity, we're not going to prove this, so I'm just going to write it out like this: sigma x equals sigma y equals minus P max times 1 minus the absolute value of z over a, the inverse tangent of the absolute value of 1 over z over a, I'll write that like this, there. And then I need a parenthesis here, and the rest I put over here. 1 minus nu minus 1 over 2 times 1 plus z squared over a squared. That's sigma x and sigma y. And because we're talking about a sphere, it's no wonder that the two are equal. So this is a sphere. X and y are exactly the same as one another. No change. Z, of course, is different from those. Sigma z minus P max divided by 1 plus z squared over a squared. Let me say a few words about again? Oh, Amber Alert. Oh, it's not a, okay. A few words about these equations. The value of z is the value of the location at which these stresses are calculated. For example, if you want these stresses at the center of the contact patch, then z is 0. If you want it a little bit further than the center of the contact patch, value of z will be non-zero. These equations are valid for both spheres. And since the two may be of different materials, then you put in the value of nu for whichever you're calculating the stress for. The pressure P max remains the same for both. If you want to find the stresses in the top sphere, you put in the value of nu for the top sphere. You want it for the bottom sphere, you put it in here for the bottom sphere. The z is the same for both of them. And notice that the maximum value of sigma z occurs at the center of the contact patch at z equal to 0. And it's equal to P max, which we expected anyway. So once again, the value of z is just a z coordinate. So z equal to 0.11 inch is maybe right there, just a little bit below the center of the contact patch. If you want it in the top sphere, it'll be a little bit above. But notice that whether z is positive or negative makes no difference here. For sigma z, z is squared, so that doesn't make any difference. For the other two, the absolute value of z over a is looked at, not the sign. So whether z is positive or negative doesn't matter. So the only thing that separates the two is nu. If the two of them are the same, then you can just take a look at one. Any questions? Okay. If you plot these stresses, the ones that whose equation I have on the board, if you plot these stresses as a function of z, so this is distance from the contact surface. So let me redraw those two here. This is z. So if you put different values of z into these equations, and you plot sigma x, sigma y, and sigma z, you get this. For sigma x and sigma y, of course, you get the same curve. They're equal. For sigma z, you get a different one. All of them are maximum at the surface of contact, at the center of the contact patch, at z equal to 0, all of them. As you get away from the contact area, all three principal stresses decrease. If the load is static, one of the things that we would like to be able to do is check for failure by yielding. And that means using some sort of a failure theory. Either the maximum shear stress or the maximum distortion energy, von Mises. And you can use either one. In the graph that you see here, a tau max is plotted. As you recall from Moore's circle, tau max is equal to sigma max minus sigma min divided by 2. This is that tau max. Remember, we have 3 of them. This is the largest of the 3. What is very important, and not something that you would guess at if asked, is that the maximum value of the shear stress does not occur at the center of the contact patch at z equal to 0. That's the maximum value of tau max. Because remember, tau max is dependent on the difference between these two, not on their absolute values. Their absolute values is maximum as z, yes, but the way they change and the way this decreases, the way that decreases, shows you that tau max, in other words, the distance between these two vertically, keeps increasing up to this point. Then from there on, it keeps decreasing. In other words, this distance again. So this tau max, the one right here, right there, is the maximum value of tau max, if that makes sense. So that point, whose magnitude is 0.3 times Pmax, this is all in terms of Pmax. Notice that at z is equal to 0, it's 1. It's equal to Pmax, which is what this equation gives you. The value of the shear stress here is 0.3 times Pmax. Other maximum stresses exist at other values of z, but they're all smaller than this. So this is the maximum value of the maximum shear stress for different values of z. This plot is for the value of nu equal to 0.3. In other words, if you put in 0.3 here and you plot, this is what you get. Put in 0.2 or 0.25 or something like that, you'll get plots very similar, but a little bit different from that, but very similar. If we are looking to see when yielding occurs or what factors of safety may exist against yielding, then we need to take a look at that and use the maximum shear stress theory and say that yielding will occur when this reaches shear stress at yield in a simple tension test, or the factor of safety is Sy over 2 divided by tau max. Sy over 2 is the maximum shear stress at yield in a tension test, which we have used often. And this is your tau max. Therefore, if given a problem and the value of nu is stated as 0.3, then we don't really need to use this equation. You can go to this graph and say, if you're looking for yielding, that the maximum shear stress occurs at 0.5a, whose value is 0.3 Pmax. Find the factor of safety. Done. If, however, the value of nu is not 0.3, it is some other value, then you essentially need to draw a graph such as this for that value and do the same thing. Or do it analytically. Find the 3 shear, in this case you only have 2 because those 2 are equal. Find the shear stress by saying sigma z minus one of these divided by 2. Take the derivative of it with respect to z, set it equal to 0, find the value of z, and if you do that for this, you'll get 0.5a. But for any other point nu, find the value of z and then put it back into this equation, to the equation of tau max equals sigma max minus sigma min over 2 to find the maximum shear stress in that case. That's how these are found. But a graph is actually much more telling than just plugging numbers into equations. Do you have any questions? Okay. This shear stress that occurs actually below the surface, so it occurs here or here, not right at the z equal to 0 mark, is cause of a lot of failures, and we'll talk about those in a few minutes. But next, let's take a look at two cylinders in contact. What's the shape of the contact patch?
An oval.
Sorry?
An oval.
Oval. Why oval?
I was thinking maybe the length of the.
That part is true. The length is true. What about the width part? Why should it be oval? In other words, if we press these two together and assume these are cylinders now, will I not get a flat area here? Rectangle, right? A rectangle. The contact patch is a rectangle. You're not that far off, because you stretch an oval, eventually you'll get a rectangle. So the contact patch is a rectangle whose length is equal to the length of these cylinders, and whose width we will calculate, or I have it on another slide. I'll show you in just a second. But one thing that I should mention before I forget is that all of the equations that we're going to talk about for cylinders in contact are valid only if the axes of the two cylinders are parallel, like this. It's not valid for this. These equations are not valid for that. The axes must be parallel. And in many instances, as much as possible, the lengths should be equal as well. That's not always possible. But if you can do it that way, it's much better, because otherwise you bring in a stress concentration factor. Once again, same type of coordinate system, x, y, z. Z is the distance from the center of the contact patch in either direction, plus or minus. That's the distribution of stress on the width of the contact patch. And it is like this, except that it's actually, this is parabolic, by the way, except that it's not spherical in the other dimension, but let's draw it someplace where, yeah, I'll draw it over here. The maximum value, once again, occurs along the center line this time of this contact area. So these are all P maxes that I'm drawing. And then they fall off as you get away from the center line. The pressure falls off as you get away from the center line. Very similar to spheres, stresses are set up in cylinders as well in both directions. other than the z direction, in other words, x and y direction. And once again, we need to find out what their magnitudes are and how we check for any type of a failure. No, actually, this was good. The top picture is the one you were looking at before. That is the half width of the contact patch. In other words, this distance here is 2b. And let me bring that up a little bit closer if you want to. Write it down, but it is in your book. Once again, in this equation, F is the applied force, or the force that's being transmitted. L is the length of the cylinder. So this is L. Nu1 and E1 are elastic properties of one of the parts, one of the cylinders, and Nu2 and E2 are elastic properties of the other one. D1 and D2, as before, are in this case not radii but diameters of the two cylinders. And everything we said about a flat plate and a trough still exists here with cylinders. Flat plate will have a diameter of infinite, and a trough will have a negative diameter. If we calculate the stresses, again, with the help of theory of elasticity, first we need to find the maximum value of pressure, and it is given by this equation, 2F divided by pi BL. That's the magnitude of this, the maximum pressure, which occurs along the center line of the contact patch. And it decreases as you get away from the center line of the contact patch. So that's your maximum value of the pressure. Sigma x, sigma y, and sigma z. And notice all three are, of course, negative. They're all compressive stresses. They're all principal stresses. Are calculated similar to what we had before. And once again, notice that whether z is positive or negative doesn't make any difference in any one of those three equations. Z is either squared or used as an absolute value. Therefore, you can use it for either of the two. What you would have to do is put in the values for that particular, or the two, not just one, the two cylinders here in calculating B. And of course, in sigma x, nu is there as well. So you need to bring in nu. Any questions? Again, all of these equations are in your book, and you should program them into your calculators for use during the exam. And while I'm on that, and before I forget, just in case you have to do that, let me show you how you should do that, how you should use the equations in your quizzes and exams. What you should not do is this. You read the statement of the problem and say equation 22, the answer is equal to 3.5, for example. Now, if you do that and your answer is correct, then that's fine. I have no problem with it. But if you don't do that, if you do that, and your answer is not correct, I can't give you any partial credit. I have no idea what you did wrong. I don't know whether you just wrote that and just say, it looks like 3.5, so I'm going to write 3.5. I don't know that. If you just made, a little silly error, for example, the number is 1.2, you wrote 0.12. That's not the end of the world. It's not a mistake you're going to make often. It's not a conceptual mistake. It doesn't say you don't understand what's going on. So if this thing has 2 points, you'll get at least 1.5 out of the 2 points. But if I don't know this, then I can't give you that. So the way you should do it is this. Equation 22, for example, says A equals B plus C. You don't need to rewrite the equation. Just say equation 22. Substitute the value of A equals 2, B equals 3, therefore C equals minus 1. That's the way you should write it. You don't need to write the equation or rewrite the equation. And you don't need to calculate it right then and there. It should be in your calculator. Put in the values of A and B and find the value of C and write it over here. Did I do that right? Yeah. That would be bad, huh? Okay. So everybody clear on this? And this is true for your equations for press fits and shrink fits as well. All of these big, long, and drawn-out equations, by all means, program them into your calculator. Don't do it every time, because it's going to take a long time if you have to use them. All right. If we now plot these equations, similar to what we did for spheres, this is what we get. Once again, all three stresses are maximum at the center of the contact patch, at the center of the contact area. That's the variation of sigma z, variation of sigma y, variation of sigma x. Once again, the maximum shear stress is drawn from these three, and notice that all three of them are principal stresses. And once again, that maximum value does not occur at the value of z equal to 0, but somewhat below the center of the contact patch, or a little bit above, depending on which one of these you're looking at. But what is different between this one and the one we were looking at is this little kink here. Why do we have that?
Changing from the difference between sigma z and sigma x to sigma z and sigma y.
Exactly. Remember that this maximum value of tau max is calculated by looking at the difference between principal stresses. Or sigma x and sigma y, same thing. From here to here, this is calculated, and you can see it here. The difference between sigma z and sigma y is very small, but that between sigma z and sigma x is large. So this is going to give you a big tau max until you get to this point, at which time sigma y is decreasing much, much faster than sigma x. And this difference, of course, is larger than that difference. That produces that little kink. So this is not a continuous function. It doesn't have one equation. It has two equations. One of them for one tau max, the other one for the other tau max. Everybody clear on this? Any questions? Now, let's see. Good place to take a break. Let's take a break, and I'll continue when you come back. To recap this, if you're given something like this, static loading, and you're trying to find a factor of safety, if the value of nu is given as 0.3, then you don't need to use the equations. You don't need to do any calculations here. You can just use the graphs and come here and take a look and say tau max occurs at 0.75 b. Its value is 0.3 p max. Calculate p max multiplied by 0.3 and you will have tau max. And then you can find the factor of safety. Oh, I erased that, didn't I? Then you can find the factor of safety using the maximum shear stress theory. Say factor of safety n equals sy over 2 divided by tau max. Now, let me ask you a question. If the problem says everything is the same as what I just said, the Poisson's ratio is 0.3, so you can use the graphs. Except that I would like you to calculate the factor of safety, not using the maximum shear stress theory, which would be like that, but using the von Mises. How do you do that? It's not in the notes anywhere, I don't think, the answer to this. In order to calculate the von Mises stress, what do you need?
Von Mises stress.
In order to calculate it, what do you need?
Principal stress.
Principal stresses. Agreed? Are these not principal stresses? So you have them. But, for example, for sigma z, what value do you pick? Do you pick the value at z equal to 0? Or some other value? Of course, whatever value you pick for z for sigma z, you should use the same value for the other two stresses as well. In other words, you should be looking at one point. And that one point will have one z coordinate. Von Mises is a failure theory that predicts yielding. Yielding requires what kind of stress? Can I yield a material by submerging it in water? Why not?
You're only changing the volume and not the shape.
Okay, what changes the shape?
Shear stress.
Therefore, we need shear stress for yielding. Therefore, if you are going to calculate the von Mises stress, for this case, you should do it at the location where the shear stress is maximum, not at the location where it's not maximum. Even though the values of sigma x, sigma y, sigma z are all maximum here. But we're not interested in their absolute values. We're interested in their differences. The differences is not maximum. The differences is maximum here. So even if it said, find this, use the von Mises stress, you still come to this diagram and you say 0.5, 0.5b. Here is sigma, which one is that? Sigma x? Yeah. Sigma x, or is that x or y? Sigma y. Here's sigma y, there's sigma x, and there's sigma z. Okay? And if nu is different, of course, then you have to use the equations, but you do exactly the same thing. You do all of it at the location where the maximum shear stress exists. Okay, one of the problems that we have, especially with this subsurface shear stress, is that once repeated a number of cycles, this leads to a failure called pitting. And you may have seen this in bearings. Bearings, for example, fail a lot like this. Gears also fail like that as well. These are pictures of actual failures. The reason for this is that the shear stress at the vicinity or in the vicinity of the point of contact or center of the contact patch changes direction as the two parts roll against one another. Let me show you this. Let's see if, yeah, this is good. Take a look at the top part first. Assume that's the driver, two parts in contact. Friction, you guys know about friction drives, right? Two parts, that one runs against the other via friction, rotates the other one. This is the driver, and that's the driven. Now, as this is rotating in this direction, trying to drive this other part, the material in here, just before it comes to, consider a point. The material at that point, just before it reaches the center line, will be in compression. Does everybody see that? Just think of, actually don't even think of them as moving. Think of it this way. I think it's easier. Assume this one is fixed. And we try to rotate that one. There's contact here, of course. Do you see that as I do this, and this doesn't move, this material in here will be in compression before it encounters the center line? And do you also see that this material on this side, this is whole area, I'm talking very, very near, but not at the center of the contact patch, that this material in here tries to pull the lower part. This tries to push the lower part, that tries to pull the lower part, so that'll be in compression, that'll be in tension. That's what you see on the screen on the top one. There, compression until this point, tension to that point. And of course it's zero right there. Neither compression nor tension. It's changing sign. As we have just seen, there are these shear stresses just under the contact area. When the normal stress changes sign from tension to compression, so does the shear stress. So if we look at the changes of the shear stress, this is what we see. See the shear stress here? Take a look at the shear stress there. In the bottom part, you can talk about the same thing for the top part. And those shear stresses have changed sign. This leads to fatigue. Because every time these two roll against one another and these 2 points come in contact, you get this reversal of shear stress. And when you get that, it leads to eventual fatigue failure. So what happens is that And this is true for cylinders as well as spheres. Due to the changes in the direction of shear stress and repetition of the shear stresses, a crack starts here and essentially propagates and just pops that little piece out. That's the essence of pitting. That's why you get pitting. It is not from just the stresses at the surface, it's from the subsurface shear stress. The variation of the subsurface shear stress is like that. As you get away from the contact patch, of course, it decreases. Comes in here, reaches a maximum there, decreases, goes to 0, decreases, changes sign.
Is it similar to like holes in the roads? Because
Insofar as the holes in the roads coming from cracks in concrete, yes. But no, the road is really not like that. There are two reasons for that. One is that the road is, of course, concrete, right? It's a brittle material. And although you do have these stresses, they're not substantial. What is it? You got a 5,000-pound car, for example, and 4 wheels. It's only 1,000 pounds per wheel divided by 4 inches squared. That's 250 psi. That's nothing. Where that comes from, more often than not, one, of course, is bad and shoddy work. Put that aside, assume doesn't exist, which it does, but assume doesn't exist. In most areas where that occurs, areas that the temperature goes down in the wintertime and there's freezing. Inherently, concrete, when it sets, it shrinks. It would like to shrink. And most of the time, since you got steel in there, it can't shrink. So minute cracks develop on the surface. When the ice on the road or snow on the road thaws, it enters these minute cracks. When it freezes, it expands and makes the cracks larger and larger, and that's what you get, those potholes. Aside from the fact that, of course, sometimes the work is shoddy. But that's one of the reasons you get those. No, it's not exactly. Although these stresses do exist exactly there, their magnitude isn't that much. Here we're talking about two very hard materials, not rubber, for example. And as you will see in an example problem, the area of the contact patch is minute. The radius is thousandths of inch rather than inches. So even though the load may not be very large, the stress is very high because the cross-sectional area is very small. Okay? We'll see that in an example. So that's what we get here. In order to analyze this and see how many of these cycles a part can take without failure, we use the equations that we had, and for cylinders, this is how we do this. We write and all of this, everything that I'm about to say is nu equal to 0.3. We write the half width of the contact patch, B squared, equal to 1.16 F over W times 1 over E1 plus 1 over E2 divided by 1 over R1 plus 1 over R2. This is the same equation we had oops, too much. Oh, it's this one here. This is this equation. It's that equation. Nu is 0.3 for both. And some changes in here. This W is the same as L. Why your book makes these changes, I don't know. But it does. I'm not a fan of it, but since it does it, so I will too. So what this is essentially, here's your contact patch. This is 2B, and that's W. If you put all of these in, put in the value for pi and all of that, that equation reduces to this, calculating B squared. Then we define, using this equation, the P max equation, we define surface strength or surface endurance, I think your book also calls it, if I remember correctly. Yeah. As that maximum pressure which causes pitting after a specified number of cycles. It is that maximum pressure that if repeated some number of cycles, and that you can define the way you wish, and we will define one, leads to pitting or failure. Notice that this is very similar to every other definition of strength. Yield strength is that stress which causes, for example, plastic deformation in the material, if that's the way you want to define it. Elastic strength is that stress which causes a nonlinearity between stress and strain. This is the same. Our pressure, of course, is that other equation, P max equals 2F divided by pi bw. Oh, this is the nomenclature for this, or the symbol for this is SC. So we use that, we use this SC. So SC equals 2F divided by pi bw. Remember, we changed L to W. In order to be able to use these equations, of course, you need to define this for a specific number of cycles. So we do that for a specific number of cycles in just a second. But before I do that, let me continue with this, and then I'll tell you what that is for steels. Oh, this, by the way, I should say this is SC is a property of the material. Just like yield strength is the property of a material. So, if we do that, we can now go into these two equations, substitute for B from this equation, and get this equation. Again, all of this is new for 0.3. 2.857 SC squared times 1 over E1 plus 1 over E2 equals F over W times 1 over R1 plus 1 over R2. Once you have selected the material, you will know the value of SC. Just like when you have selected the material, you know the value of yield strength, tensile strength, modulus. So taking a look at this side of the equation, property of the material, property of the material, property of the material. Remember, you have two pieces in contact, so E1 and E2. Both of them have nu equal to 0.3, however. Therefore, the expression on the left-hand side of this equal sign, which we call K1, Buckingham's constant, is a property of the material. Once you have selected the material, K1 is known. The value of SC I'll talk about in just a second. So it's just like saying, therefore, yield strength is equal to the load divided by the cross-sectional area. This is nothing but a stress, actually. It is very, it's not exactly that, it's very similar to that. So when this equals that, the material can take whatever this number of cycles for which we defined SC. And you define that for whatever number of cycles you wish for whatever material. In particular, the one that we use here is steel. And for steels, we have an equation that can give us the value of the surface strength. SC, this is for steels. SC equals 0.4 HB minus 10 KSI, or 2.76 HP minus 70 MPa. In this equation, you need an equal sign there. In this equation, SC is the surface strength, HB is the Brinell hardness for the material. And if you know your material, you can either find its Brinell hardness from a table, or if you don't have a table of Brinell hardness, but you do have the tensile strength of the material, steels again, there's this approximation that SU equals 0.5 HP in KSI, and SU equals 3.5 HP. I'll check this one in MPa. These are in your book on page 52, I believe. Page 52, equation 221 for steel, and they have another equation for cast irons as well. And they use 3.4 rather than 3.5. These are approximate equations. These are not exact equations. So I should put that approximate sign there. And you had a situation to actually do this, find this relationship when you did tension test in 220. You guys run a hardness test, right? Did you run a hardness test? You didn't run a hardness test? How did you know, or did you know, what the tensile strength approximately would be, so you would set the dial on the machine, or you don't even work with dials anymore? You just push buttons and a number comes out. So you guys, I'm surprised that you say none of you did hardness tests, because in the other section I had at least a few people nodding like this, that they had done hardness tests. So if you want to know a little bit about hardness tests, let me know and I'll tell you a little bit about it. But read up on it. It is an extremely important property of the material. Very easy to find, very easy to find. Off of it you can get the tensile strength. Off of tensile strength you can get the yield strength. These are all approximate values for a ductile material. And from that you can get what is called endurance limit, which is the strength of the material in fatigue, and that we're going to go over extensively later on. So once you pick your material, presumably steel, you use that equation to come up with the value of SC. So you have this. Now if you want to use a factor of safety, this is for, oh, I should say this as well. For 10 to the 8 cycles. Very important. So once you have found the value of SC, you put that into this equation, and you find the maximum load that may be applied. The equation, of course, is this. K1 equals F over W times 1 over R1 plus 1 over R2. How do you incorporate a factor of safety into this equation? Does this look like any other equation you know? How about this? Isn't that the equation for finding a load at yield in a simple tension test? Okay, how do you incorporate a factor of safety here? Again, I hope you're just bashful. Otherwise, things are not good. You either multiply that by the factor of safety, let's say 2, or you divide that by 2 and solve for the force. You say Sy equals 2F divided by A if you want a factor of safety of 2. Or Sy over 2 equals S over A, F over A, sorry, and solve for the value of F. We do the same thing here. So you want a factor of safety? Just like you divide Sy by N, divide K1 by N. Once you find the value of K1, the value of the factor of safety, it will tell you whether this will last 10 to the 8 cycles or not. And if it doesn't last 10 to the 8 cycles, you can't use this equation to find how many cycles this lasts. You have to go back, redo the problem for another number of cycles until you get to a point where the factor of safety comes out to be 1 or close thereto. Then you say this is the number of cycles. But we don't do that. We usually say, will it have a life of 10 to the 8? The answer is either yes or no. And it depends on whether this value of n is greater than 1 or less than 1. Okay? Any questions? Okay, let's take a look at an example problem. This is in your handout. So take a look. We read together. In a traction drive, a 1.0-inch diameter cylindrical roller is preloaded against a 3.0-inch diameter cylindrical roller. The steel rollers are 1 inch wide and the preload force is 50 pounds. The axes of the rollers are parallel, as they should be for us to be able to use these equations. Calculate the maximum contact pressure and the width of the contact area. Also find the maximum value of the subsurface shear stress. So here we have made some assumptions here, and if you are lacking some information in a particular problem, make the most logical assumption that you can and solve the problem. Don't say, I don't know what nu is. For most metals, for example, nu is somewhere between 0.25 and 0.35. There are some exceptions, but in general, that's it. That's why we always take it as 0.3, because that's a good middle value. So here we are assuming both of these are steel. The rollers are. There's E1 and E2, 29 times 10 to the 6 psi. Nu is taken as 0.3, so we can use the graphs rather than the equations. Yield strength 60 ksi, tensile strength 90 ksi. This is just a regular steel, nothing major. It's not a high strength steel or anything like that. B is the equation that we have before. Notice that we have everything. You have the load, 50 pounds, length, 1 inch, nu1, E1 for the two, nu2, E2 is given, D1 and D2, the diameters are 1 inch and 3 inch. So you substitute, and that's what I meant when I said that these areas are very, very small, 1200 microinches. 0.001 inch is the width of the contact patch. So even though the load is just 50 pounds, the stresses are high. And that's why you get the failures that you do. P max, again from the equations that we have, 2F divided by pi BL, 26.6. Since nu is 0.3, we can use the graphs, these graphs, and recall from those graphs that the value of tau max is 0.3 P max, and it occurs at about approximately 0.75 B. So we find the maximum shear stress. And according to the maximum shear stress theory of failure, factor of safety is shear stress at yield, that is yield strength divided by 2, SY over 2, divided by the shear stress that you have. Factor of safety, static factor of safety, 3.8. Continuing the problem, we say, what is the factor of safety against a life of 10 to the 8 cycles? So we use Buckingham's constant. And first we must find the Brinell hardness. SUT is 90. In the previous edition of your book, this was 0.45. They are now using 0.5. This 0.5 is much more reasonable value. These are all approximate, and having two significant figures makes no sense. But since that was what they were using, that's what I've used here. So if you got 0.45, either leave it that way, leave yourself a note and write, it's 0.5 now, or just keep it in the back of your mind. So there's the Brinell hardness. Use this equation to find SC, 70 KSI. Use the equation for Buckingham's constant to find K1. And finally, use this equation to find the factor of safety. So you got to go from the material to essentially the strength of the material and equate it to the stress in the material. In layman's term, in a very easy term. So we get a factor of safety of 7, so the answer is yes. This will last 10 to the 8 cycles. In calculating all of this, we have neglected the shear stress that exists at the surface of contact when these two rub against one another. We've neglected that shear stress here. But that's what we usually do in these problems anyway. Any questions? Okay, that concludes contact stresses. Now we'll go to a subject that either you guys like very much or hate very much, and nothing in between. Energy methods, and then we'll take a look at Castigliano's theorem as well. When we were talking about failure theories, we mentioned that when a force acts on a body and that body deforms in the direction of the force does work. And that work is changed, that work will change the energy of the body. Potential energy, kinetic energy, and if the body is stationary and is not moving up or down, doesn't have a velocity, then it is stored as strain energy in the body. The work done by an object, by a force, on an object, in general, is the integral of p dx, where p is the applied force, and dx is the displacement in the direction of that force, the increment of displacement. This, of course, represents the area under the force displacement diagram. So there's your equation, and that's what it indicates. That's the integral of p dx from 0 to whatever value of x you would like. If that relationship is linear, like that, then the work done can be actually calculated as p1 x1 over 2. We looked at this when we did when we did failure theories, von Mises to be exact. Now, we need to calculate the total strain energy in the material. And the total strain energy is essentially this, the work done on the body. And it depends on the dimensions of the body. Is everybody okay with that? It depends on the dimensions of the body. For example, take into consideration if I apply the same force here as I do to this one, and if except for the length, all of the dimensions are the same, which one of these will deform more? The one on the right or the one on the left? Change of length is larger in which one? Change of length is equal to? Come again, please. PL over AE, very good. PL over AE. But let's see where that comes from. Change of length is equal to the strain times the length, right? Strain, if the material is acting elastically, is sigma over E. And sigma is P over A. So it's PL over AE. Since everything is the same here, cross-section is the same, the load is the same, the stress is the same, therefore the strain is the same. So in one case you multiply it by L, in the other case you multiply by 2L. So clearly the one on the right-hand side will deform more. If it deforms more, means that's larger. If that's larger, then we get more work, more energy. So energy is a function of not just the applied load and the material, but also of dimensions. And the same is true if you change the area, of course. Doesn't matter. So in order for us to be able to compare those two, we have to take out, if these, for example, were made of two different materials, we have to take out the effect of volume, dimensions, that is. So what we do, and again, very similar to what we did in failure theories, rather than looking at the total strain energy, we look at strain energy density. Everybody remembers that? That's strain energy per unit volume. So, as you see on the screen, we divide the total strain energy by the volume. And in this case, I've simplistically taken the volume to be equal to AL. That means I've assumed the cross-sectional area to be a constant. That's not always the case, and we'll look at cases where this is not the case. But just very simplistically, there's the volume, there's the work. P over A gives you sigma. The X over L will give you d epsilon x, the increment of strain. Therefore, the strain energy density is the area under the stress strain diagram. That's the area under the stress strain diagram to whatever strain you are creating in the material. That's a general equation, and it's valid whether or not the material is acting linearly elastically. You just substitute for sigma x, whatever the function is. Do we have materials that don't act elastically? You know at least a few, all of you. Maybe didn't think about it, or it wasn't mentioned, or anything like that. But have you ever stretched a rubber band? Initially, it's very, very easy to stretch. You get to a point where it's actually very difficult to stretch it anymore. That's near the failure point. So that certainly is not a linear relationship. In fact, for a rubber band, doesn't go back. It's like that. However, that relationship, even though nonlinear, it is elastic. It will come back to its original length, but it won't come back along the same loading line. It'll come back along this line. That's the unloading line. And if this is the strain energy that we stored in the material, when we unload it, we're not going to get all of it back. The area in between those two lines, that's what's lost. Where does it go? Heat. Rubber is made of very long, not that this is a part of stress analysis, but it's good for you to know. It's made of very long chain molecules. And when you stretch it, these molecules rub against one another, create friction, which creates heat. You can test this very easily. Take a rubber band, load it and unload it about 5 to 10 times, and put it to your face. You will feel the warmth. The rubber warms up. That's due to that lost energy. Okay, so it's a little bit about this. But in our case, mostly metals, stress-strain relationship is linear. So we substitute for that in a linear relationship. And what we get here is that the strain energy density, and I think I've corrected all of these subscripts and superscripts in your notes. They're not as bad as they look on the screen. These are all, this is a subscript and that one is a superscript. So we get sigma squared over 2e. This only indicates that the stress is in sigma x, doesn't matter. This is true if we have this relationship and if the value of the stress is uniform, it's not changing. It's the same for all points. For example, it's like this. Value of the stress is the same at all points. But it doesn't have to be. The value of the stress may change because this may start with one cross-sectional area here and end with another cross-sectional area here. So over here, I divide P by a small area. Down in here, I divide P by a large area. So the value of the stress doesn't need to remain a constant. If it doesn't, then use the limit of delta U delta V. As delta V approaches 0, we get du dV. That's the equation that we are going to use in order to find the strain energy density in various parts. Oops. So, for a variable sigma, let me make that bigger. In the case of variable sigmas, we use the previous equation that U equals du dV in that form. U equals, therefore, U equals the integral of U, little u, strain energy density, dV, like that. And in the linear elastic case, sigma and epsilon are related via E, the modulus of elasticity. And so we input for sigma x, we input, we'll just call it sigma because it's good for all directions, E epsilon. And then that integral will be that U is equal to the integral of sigma x, which is E epsilon, d epsilon. And now you can integrate it. And this is equal to E epsilon squared over 2. Now you substitute for epsilon sigma over E, and you get that equation, sigma squared over 2E. Or you substitute for E sigma divided by epsilon, you get sigma times epsilon divided by 2. That equation. So these, all three equations are the same by various types of substitution. So the total strain energy is this. General equation applies to all stresses. In particular, let me see how much time I have. Well, I have 4 minutes. I can do this one for you in 4 minutes. Not a big deal. For example, we apply that equation, and remember what the equation is. Sigma squared over 2e divided times dv, and you take the integral of it. Repeat it here again. Axial loads. And now the cross-sectional area is not a constant. It changes. The integral of u dv, integral of sigma squared over 2e dv, that's the previous equation that we had. Sigma is P over A. It doesn't matter that A is changing, but sigma is always equal to P over A. You want to find it here, you divide it by this area. You want to find it here, you divide it by that area. I want to find it there, I divide it by that area. Sigma is not a constant, but it's still equal to P over A. So you're getting P over A. Put it into that equation, P squared 2A squared E dV. And with dV equals A dx. A times dx. This is the element that we are taking for our integral, for our dV integral. So put in A dx rather, into this equation. You'll get that. Integrate it, and you will have the values. Of course, you can't integrate that unless you know the value of P or whether or not it's a constant. In this case, it is a constant. But you also need to know how A changes with respect to the length. You need to know that, otherwise you can't evaluate this, because A is not a constant. It is a function of x. However, if P and A are constants, then P and E, all of them will come out of the equation, and the x is from 0 to L essentially becomes L. This is the strain energy, total strain energy, that's stored in the material if it is something that's loaded like this. Constant area, constant load. Okay? That must be equal to the work done on the material. Is it? The work done on the material is? Right? Where E is the change of length. And we just got done saying that change of length is PL over A. So we can put that in there. For constant load and constant P, this becomes PE over load, PE over 2. So P times PL over AE over 2 equals U. And that's what you get there, and that's what you get by multiplying P times E and dividing it by 2. And of course, that should be the case because that's where the strain energy comes from the work done on the material. Okay? Any questions? All right, that'll be all for this week. If there is a quiz on Tuesday, it will not cover this. I haven't said very much. So it'll be just on the rest of the stuff that we've had. Have a good weekend.